Hello everyone, this is Dr. Mo Shiva, Professor of Electrical Engineering at California State University, Fullerton. Purpose of this video is to do a review of nodal analysis with the assumption that you're familiar with basics of it. This is the second out of 3 videos for nodal analysis. If you have not seen the first video, please go back and review that before continuing with this example. A lot of basics and the highlights of nodal analysis were covered in the first video. So, to do a quick review, we take the following steps in nodal analysis. First thing, always simplify the circuit. We don't want corners like that to exist in the circuit. Just make it as simple as possible. Then we choose a reference node, which for this problem is already given. Assign voltages to non-reference nodes. And the difference between this and the previous example mainly is we have a voltage source present in the circuit. And with voltage sources for nodal analysis, we have to use supernodes. As I mentioned several times in the first video, the best version of Kirchhoff's current law is to use summation of currents leaving a node equal to 0. We are using passive sign convention, which means if you have a resistor with resistance R, voltage V, and current I, as shown, then we look at voltage drop across the resistor being equal to resistance times current entering positive side of V, positive terminal of the voltage. With that, current would be V over R. So, looking at the circuit, we want to find nodal voltages and power supplied by each source. We have a voltage source, so we have to use a supernode. First step, as I said before, is to simplify the circuit. So we simplify the circuit, get rid of square corners. We have reference at the bottom with 0 volts. We have nodes V1, V2, V3, nodes 1, 2, 3, and 4 with voltages V1, V2, V3, and V4. And since we have a voltage source between nodes 3 and 4, we combine those into a supernode. Inside the supernode, we still have V3 and V4 that we use. We use summation of currents leaving the node equal to 0. Let's start with node 1 and current going down. Start with one of the branches and go either clockwise or counterclockwise so we don't miss any of the currents. Next current going through the one on right there between node 1 and 2. And finally, we add the current going through the top resistor. So for node 1, we have -6 plus current going from node 1 to node 2, positive on node 1, negative on node 2, the voltage that we need is V1 minus V2 over 1. Current going from node 1 to node 4 is V1 minus V4. We need plus on the left side of the 1, negative on the right side, divided by 1 equal to 0. Let's go to node 2. Current going straight down at node 2 is V2 over 1. Move clockwise. Next, we want to look at the current going from node 2 to node 1. So voltage would be V2 minus V1 over 1 gives us the current. Current going to the right is V2 minus V3 divided by 1, and they should add up to 0. A supernode. Supernode includes nodes 3 and 4, 3, 4. So let's start with the current going left from node 3 to node 2, and then we go clockwise along the red line to get the other terms. So first term is V3 minus V2 divided by 0.5. And next on the top we have V4 minus V1 over 1, and finally V4 over 1 equal to 0. And when we use a supernode, we look immediately inside the supernode. In other words, the information provided by the voltage source. That voltage source is telling us V4 on the right, positive sign, on the left, negative sign. V4 minus V3 should be equal to 3 volts. Advantage of using currents leaving the node is for Kirchhoff's current law, we can quickly check for a sign mistake. For node 1, we should have positive V1 minus something. Positive V1 or positive V1 minus something. So check quickly for a sign mistake. For node 2, we should have either positive V2 or positive V2 minus another voltage. Supernode is nodes 3 and 4, so basically follow the same rule. We need positive V3 or positive V4. This way, if we have made a sign mistake, we can quickly find it and correct it. Now we have 4 equations. Let us simplify those. Simplifying the equations, we have 2V1 for the first equation minus V2 minus V4 equal to 6, negative V1 plus 4V2 minus 2V3 equal to 0. The main step is writing the equations correctly. Solving it is just standard system of equations, linear system of equations. Negative v1 minus 2v2 plus 2v3 plus 2v4 equal to 0, and negative v3 plus v4 equal to 3. 4 equations in 4 unknowns. Kramer's rule would be extremely lengthy, so let's try elimination of variables. From last equation we have v4 equal to 3 plus v3. Put that in the previous equations. We get 2v1 minus v2 negative minus 3 plus v3 equal to 6. Negative v1 plus 4v2 minus 2v3 equal to 0. That doesn't change. And last equation, or third equation, negative v1 minus 2v2 plus 2v3, and here we get plus 2 times 3 plus v3 equal to 0. I'll simplify those. Two v1 minus v2 minus v3 equal to 9. Let's call this equation 1. Negative v1 plus 4v2 minus 2v3 equal to 0. Let's call this equation 2. And last equation, we get negative v1 minus 2v2 plus 4v3 equal to negative 6. Call this equation 3. Again, we can use Kramer's rule at this point, but we get 3 by 3 determinants. So noticing that we have nice coefficients for v1, let us eliminate v1 and get 2 equations in terms of v2 and v3. So take equation 1, its coefficient is 2, multiply equation 2 by 2, so we get negative 2v1, and add it to equation 1. So equation 1 plus 2 times equation 2 gives us 7v2 minus 5v3 equal to 9. Let's call this equation 4. And let us get equation 1 and add to it twice of equation 3. Gives us negative 5v2 plus 7v3 equal to negative 3. Next, let's eliminate v3 in these 2 equations. Let's get rid of v3. Make the coefficients of v3 equal. So multiply that equation by 7, and let's multiply the second equation by 5. We end up with 49v2 minus 35v3 equal to 63. negative 25 V2 plus 35 V3 equal to negative 15. And if we add this up, V3 will cancel out. We end up with 24 V2 equal to 48. So we have V2. V2 is equal to 2 volts. From equation 4 right above, we have 7V2, 7 times 2, minus 5V3 equal to 9. So 5V3 is 14 minus 9 equal to 5. So V3 is 1. Let's find V4. Up here we had V4 equal to 3 plus V3. So let's use that. So V4 is 3 plus V3, resulting in 4 volts. Use equation 2. V1 is 4V2 minus 2V3, 8 minus 2, 6 volts. So we have the nodal voltages. We want to find the power supplied by the sources. For power, we commonly use passive sign conventions again. Power is voltage times current, and what that means basically is absorbed power by the element is voltage times current entering positive terminal of the voltage. Problem is asking for supplied powers. So let's look at the sources. For the 3 volt source, the supplied power would be 3 times. Since we are looking for the supplied power, let's find it directly. Let's look at the current leaving the positive, and let's call that I1. So it would be 3I1. Notice that I1 splits, goes up and down, or we can also use the fact that I1 is the same current that is going from node 2 to node 3 through 0.5 ohm resistor. So I1 would be same as this current. So if we just say power, we are always talking about absorbed power. So power for 3 volt source, let's make sure we notice this is supplied power, is 3I1. That is 3 times node 2 to node 3. Current going from node 2 to node 3 is V2 minus V3 over 0.5. So we get 6 times 2 minus 1, 6 watts. And make sure you put sublight next to that. Otherwise, when we talk about power, we're simply referring to absorbed power. For the 6 amp resistor, V1 represents voltage drop from the top to the reference. So 6 amps is already going out of its positive. So sublight power for that would be 6V1, that is 36 watts, and make sure again you put the word sublight next to it. So that is how we solve problems which include a voltage source. Voltage source dependent or independent, doesn't matter. We always use a supernode. I'm going to do another example, video 3 or example 3, a little bit later. Make sure you review this example and then check the third example for nodal analysis. Thank you.